Welcome to Sequence, Key, and Index Creation lesson. Today we are covering these database objects that are intimately related to tables that we discussed previously. We'll start with sequences, what they are and how they help database applications with auto-sequence numbers. Next, we'll check out keys, primary keys and foreign keys, which are subcategories of constraints, but which could also be linked to indexes, the next and last topic in this lesson. With indexes, we'll just scratch the surface as we'll leave more complex details and algorithms to a dedicated advanced lesson. Sequences in PostgreSQL are special single-row database objects that generate unique numeric values. They are commonly used to create unique identifiers and implement columns. The basic syntax for create sequence command is create sequence, a sequence name, and let's break down each component. Increment by specifies the step between consecutive values. Can be any positive or negative integer number. Of course, 1 is the most common one. Start with sets the starting value. While 1 is again the most common, you can determine a different number to begin with. Higher numbers are typical for descending sequences. Min value and max value define the boundaries of the sequence, so next values will never go beyond them. By design, max value must always be greater than min value. Otherwise, your create sequence will raise an error. Min value must be less than max value. Cache pre-allocates numbers for better performance. Something like 20, for example, will make Postgres cache the next 20 values of this sequence, so it doesn't need to recalculate on every call. Although it might seem simple, this can improve performance, especially for write-intensive applications where several records are created in a short period of time. The drawback of this approach, which is usually not a big deal, is sequence gaps that we'll cover in a bit. Cycle and no cycle determines behavior when reaching max value in ascending sequences or min value in descending sequences. Cycle returns the sequence to the order value, while no cycle raises an error on every next call until you either restart the sequence, force its current value, change the boundaries, or change it to cycle. PostgreSQL provides 4 main functions for working with sequences: nextVal and sequence name, advance the sequence and returns the new value. This is where all the magic we explained before happens. CurrentVal in the sequence name returns the most recently obtained value from nextVal in current session. LastVal returns the value most recently obtained with nextVal for any sequence in the current session. So that's why we don't specify any sequence name for this command. SetVal with sequence name, value, and optionally an isCalled Boolean parameter. It sets the sequence's current value. The third parameter determines whether the value is considered called. When this parameter is true, which is the default, the sequence is marked as having returned the value. So nextVal will return the next value after that, not the one just set. When set to false, the sequence is set to return the specified value on the next call to nextVal. SetVal is particularly useful in a few different scenarios. One is restoring data from a backup, for example, where explicit ID is defined and we need to update sequences accordingly. Otherwise, sequences would return an ID that's already taken. Fixing gaps in sequence values. Resetting sequences for testing environments. There are 2 important aspects to highlight in terms of sequences. The number one is sequences are session-based. This means that if a user A session requests nextVal of a sequence, user B's concurrent session, when also calls nextVal on the same sequence, will not only get the next value but also shifted by all values cached by the user A session. And number 2, sequences are not transaction safe. Sequences are actually used to provide transaction safe values. Therefore, they are never rolled back, even if a transaction fails. This behavior is different from some other database systems like Oracle, where the sequence cache is shared globally. In PostgreSQL, each session gets its own cache to improve performance and reduce contention. This design has some important implications. It can lead to gaps in the sequence, like we discussed before, especially if sessions end without using all the cached values. It allows for better concurrency, as sessions don't need to wait for each other to access the sequence. The order of sequence values doesn't necessarily correspond to the order of transactions or inserts. While this behavior might seem unexpected at first, it's intentional. It helps PostgreSQL maintain good performance for sequence operations. Serial is not actually a true data type. When you create a serial column, PostgreSQL does this automatically. First, it creates a sequence object named table name underscore column name underscore sec. Second, it sets the column default to the next val of that sequence. And third, it marks the column as not null. Here is what happens behind the scenes when you write a create table products where the product ID is serial. PostgreSQL actually executes these steps. First, it creates the products underscore product underscore ID underscore sec. And nothing else, because all parameters we discussed defaults to a simple one-by-one ascending sequencing. Second, it runs the create table products as its product ID column was written like integer not null default next val of the created sequence. Third, alter, a command we'll discuss in next lesson. Alter sequence, the sequence name, then owned by the serial column prefixed by its table name. This command creates an association between the sequence and the specified table column. This owned by clause essentially tells PostgreSQL that the sequence's lifecycle is tied to the specified column. Without the association, the sequence will remain in the database even if the table or the column it was designed for is removed. While serial types are convenient, they are gradually being replaced by the SQL standard identity columns. Identity columns provide a SQL standard way to automatically generate unique values using an implicit sequence. They offer more control and standardization compared to PostgreSQL-specific serial type. These create table users, instead of user ID being a big serial, it is a big int complemented by generated always as identity. PostgreSQL provides two generation modes: generated always as identity, which rejects explicitly provide values, and generated by default as identity, which similarly to serial columns accepts explicit values when provided. Think of generated always as a stricter version that ensures all values come from a sequence, while generated by offers more flexibility. Behind the scenes, everything else is like serial types. Something like insert into users and then username. Look, we didn't provide the user ID, then the value Alice, for example. This works just fine in our generated always as identity, big int column. The second insert is equivalent, as we explicitly asked PostgreSQL to provide its default value, which is the next of our sequence. The third command, on the other hand, fails with generated always as identity. While serial remains widely used in existing PostgreSQL databases, identity columns represent the SQL standard approach and are recommended for new applications. Keys are fundamental constraints that ensure data integrity and establish relationship between tables in PostgreSQL. Let's take a look at primary keys. A primary key uniquely identifies each row in a table. It can be implemented at both column and table levels. In the column level syntax, you define that the column is the table's primary key right next to the column name and the type definition. Using the table level syntax, you define it after all column definitions. The same syntax for all the table level constraints. So constraint followed by its name, then primary key, but as we are no longer next to product ID, we need to specify the product ID within parentheses. You might be thinking, what's the advantage of table-level syntax? Well, in this example, not much. PostgreSQL default names for primary keys are pretty good. However, remember, table-level constraints give you freedom to refer multiple columns. And when we have multiple columns, is what we call composite primary keys. In this example, what uniquely identifies an order item, which is where we store all items purchased by a single order, is not the order ID or the product ID. It's actually both combined. So the constraint in this case comprises order ID and product ID combined. When creating a primary key, first of all, Postgres automatically creates a unique B-tree index. More details in section 6, performance and optimization. Second, enforce both not null and unique constraints, so you don't need to add them. Third, only one primary key constraint is allowed per table. And like we said before, it is the way you can uniquely identify a record in your table. Foreign keys establish relationships between tables by ensuring referential integrity. They prevent actions that would destroy links between tables. Using the basic column-level foreign key syntax, the orders table is created with custom ID and the keyword references followed by customers, which is a customer table, and one of its unique colors in the parentheses. You're right in expecting custom ID to be the primary key of customers table. However, technically, it only needs to be a unique column. So that's a way you can refer a unique record from the other side. Using the table-level syntax, we define the constraint followed by the constraint name, then foreign key, with the local foreign key column in the parentheses. Again, because you're no longer writing these next to the column we refer to. Finally, the same references as before, customers table and its custom ID column. By the way, the columns don't need to have the same name in both tables, orders and customers. PostgreSQL provides options to handle different role modifications. One of them is restrict, which prevents deletions of reference rows. Another one is cascade, that automatically deletes dependent rows. Other one is set null, which sets the referencing column to null. And finally set default, which sets the referencing column to default, which could be null. One example of these options could be the same customer ID foreign key we saw before, but now using onDelete set null, which means if a customer reference by an existing order is deleted, all other records that contain that customer ID will be updated to remove this ID, not the record itself, as the ID no longer exists. This is purely a business-driven decision. We could have chosen something like restrict, to have an error basically say, hey, you can't delete a customer that has made orders because orders are important for our records. Do something else like set a flag like is deleted to true, but never physically delete them. We could have also set a cascade, which is exactly what we decide to do with onUpdate. Well, if custom ID is an auto-sequence number, we most likely never need to update. But imagine we decide to use a business provide custom ID. Also imagine the business coming back saying, hey, all existing customer IDs will increase a digit, so we need to update the existing ones with this digit. With onUpdate cascade, the updates on customers table will automatically reflect in orders table. These options help maintain data consistency when parent records are modified or removed. We'll explore how these onDelete and onUpdate options interact with delete and update commands in a future lesson, data modification and deletion. In the relationship types we've touched on here, we'll be exploring depth during session 4, where we'll learn everything about database design patterns and normalization. While we'll focus on tables and constraints, PostgreSQL provides another critical database object type, indexes. Indexes are special lookup structures that improve query performance by allowing the database to find data without scanning entire tables. Think of indexes like the index at the back of the textbook. They help you quickly locate information without reading every page. The createIndex command creates an index on one or more columns of a table. For example, an index on products, column name, can speed up searches by product names, while indexes on orders with the combination of custom ID and order date could also save us time if we need to regularly search for customers' orders in particular dates. When you create a primary key or unique key constraint, PostgreSQL implicitly creates a unique index on the constraint columns. These indexes enforce the uniqueness requirement while also providing query performance benefits. Foreign key constraints, however, do not automatically create indexes. You may need to create these manually for optimal performance. These automatically created indexes follow specific naming conventions, typically using the constraint name. On PSQL, you can list indexes by typing \di or view more details by querying the PG index system view. Like for example, in this query, we have a select index name index depth from PG indexes where a table name is products. So it lists all the indexes related to this table. Let's put everything together by building a simple order management system. You can copy these commands from resource materials, but I prefer you to give it a try, as it's the best way to learn and fix. This structure ensures data integrity while maintaining flexibility for future modifications. Notice how the constraints work together to prevent invalid data entry. Remember, while these examples demonstrate the technical aspects of table creation, in real-world scenarios, you want to spend considerable time planning your database structure before implementation. And that's a wrap. Now you know how to create all database objects that are used in probably 100% of all relational database in production environments out there. There are more, but you now know by far the most common ones. In next lectures, you'll see how to manage them, while we'll learn other DDL commands, alter and drop. See you then.